everybody, thanks a lot for coming. This is UAV Plus. And we have two special speakers today. We have Niels Joubert from here from the CS department here in Stanford. He's researching trajectory optimization for cinematography. And so part of that and the practical extension of that after you do all the simulations and optimizations is to actually go and fly a quadcopter with a camera to see if those trajectories that you optimize make sense. And so it's, as an extension of that, he's had to deal with something called differential GPS, a way to make more accurate positioning, to get a more accurate position. And so that's what he'll talk about today. We also have a representative from Lilly, and we don't know if he actually showed up yet. No?
I don't see him.
Somebody from Lilly here? No? Okay. Well, maybe he'll show up while he's at any rate, we're happy to have Niels talk to us today about the cool stuff he's been doing. And this is like a quick primer on how do you make accurate position data for your quad.
Sure. Thanks, Trent. So I know a bunch of you guys, and for the people I don't, hey, pleased to meet you. I'm Niels. This talk is one of two talks, and so this is going to be more of like a rough and ready overview of how GPS works in like, I was told I have like 15 to 20 minutes, which is far too short to get into any of the like complicated, detailed, technical stuff, but it's enough to kind of give you a working man's knowledge of here's all the parts of that makes GPS work, and most importantly in my mind, it's where do we get the accuracy or inaccuracy from, and what can we do about that? Because hopefully, like, my audience here is probably, I guess all of you guys fly quads or fixed wings or something. Who here flies some kind of UAV? Okay, so pretty much everybody. Well, at least more than half the room for sure. So hopefully, at the very least, what you'll get out of this is like, here's a couple of pointers on how to get the best performance out of your GPS system and understand the reason behind those pointers. And then Trent and I were talking about in the future, I can also then come in and do like a version 2 of this, which will talk in detail about the math behind doing differential GPS. And I believe the Lilly people just arrived. Yeah. So anyway, good. Just in time. I'm just getting started. And so my interest in this, as Trent was saying, is I'm in the CS department. I'm a computer graphics guy, and as part of doing research on camera placement and optimizing camera trajectories, we said, well, okay, we need to be able to localize our quads really well. And through a long series of events, I'm now working part-time with Swift Navigation that is building a centimeter accurate GPS. So let's get started. First of all, where am I is a fundamental question that your UAVs are asking, right? Like, what can we do if we can do good localization on quads? It seems that this is interesting for most autonomous missions. There's plenty of things you can do, actually, that doesn't involve knowing where you are. But many of the interesting problems do. So two big ones that I'm interested in is precise trajectory following in like unconstrained outdoor environments. So you've seen plenty of indoor versions of this where people use things like motion capture systems or visual tracking or LiDAR or what have you to do very, very precise localization of a robot indoors. Outdoors is a little bit more challenging, and GPS is pretty much one of the best cheap systems currently available. Another thing that's very interesting is doing precise waypoint flying, because this will allow you with fixed wing aircraft to do things like precise autonomous takeoffs and landings. And I think probably for this audience, that's probably all interesting motivation. So my solution to this was to say, okay, I think GPS is the way to go. So let's look at what's available on the GPS side. Many people think GPS and they go, yeah, there's a bunch of satellites up there. Guess what? Like, big government agencies spends a lot of time and money putting these up there. And so practically speaking, there's two big systems currently flying. One is the US's Navstar GPS system. It's got 28 active satellites. They're sitting about 26,000 kilometers above the surface of the Earth. And here's an interesting number. They take about 12 hours to do a complete orbit. Why is that interesting? Well, that means that it takes about 6 hours for a GPS satellite to come over the horizon, go all the way up above me and set. Of course, it's less if it's very low orbit from where you are on the planet. So here's a first interesting little tidbit. The accuracy of your GPS fix obviously depends on all the satellites you can see, and that changes on the order of half an hour to an hour. If there's a satellite on the horizon, it might come up, be visible for 2 hours, and then set. And so when you work with GPS, you basically want to be aware of how your GPS constellation is changing over time. 28 satellites in the US one, 24 in the Russian one, and then there's actually several other ones also. I've listed some of them here. The European Union is busy putting one up. China has one that mainly covers Asia Pacific. Japan has their own 4 satellites that covers only Japan and the surrounding areas. And India is also busy putting up one. Why is it good that there's so many satellites? Well, I'll explain in a second how the more satellites we have, the better accurate, the higher accuracy fix we can get, because we can get rid of some of the noise, some of the interference issues between multiple satellites. So it's good for us. There's more and more satellites going up, which means better precision GPS, better availability, better coverage for the whole world. So how does GPS work? In an attempt to understand my audience a little bit better, who here can actually explain how GPS works right now?
To what extent?
Like, if you were to given 15 minutes and like a marker, could you not do the math necessarily, but could you just kind of sketch out, here's all the component parts? Okay, so for you guys, this might be very elementary, but luckily there's enough people that I think this might be useful to get something out of. And for the rest of you guys, bear with me and feel free to ask me questions, or if I like say something grossly incorrect, just keep it to yourself. But to start off with, it's a very simple idea. It's time of flight range. So for you guys that have read the Understanding GPS book by Kaplan, these figures are from that, so it'll be familiar. So suspend your disbelief for a second and just imagine we're on a ship, okay? And we all agreed that Trent is standing on the shore at the Golden Gate Bridge. We synchronized our watches and we said, once a minute you're going to blow the foghorn. Now we're out in the fog somewhere, we can't see anything, but I look on my watch and I go, okay, it's my second hand just hit 0, so I know Trent's blowing the foghorn right now. And then I count and I go 1, 2, 3, and I hear the foghorn. So I go, okay, took 3 seconds for the sound of the foghorn to radiate in a perfect circle at a constant speed from him and then hit me. So if I know how long it took, 3 seconds, and I know how fast sound moves, about 300 meters per second. That's a huge approximation. Now I know how far away I am from him, right? So what if we had a lot more buddies? What if we had like 3 people standing on different points of the shore? If we knew where they were and we timed all of their signals, then now we can calculate the ranges to all of them, right? Does that make sense, right? So pretty simple. All we have to do is agree on a time and know where you are, like where these base stations are. And then I measure the time it takes for a signal to get to me, calculate the range to it, and then I can just say, well, if I assume that signals travel in a nice sphere like this, I've got the ranges, I can draw the circles, and I'm at A. So easy, right? That's pretty much the end of the talk, right? Because that's all there is to it. Right? This is how GPS works. What's challenging here? What's the big assumptions? Well, I had to know where my base stations are. Okay, how do I do that? We had to agree on a time. That seems challenging. Like how does my phone know exactly what time it is compared to the satellites? And I had to be able to time radio waves really accurately. So how fast does radio waves move in a vacuum? Well, about 300,000 kilometers per second. Okay, that's pretty fast. And of course, with all those assumptions, that means we will introduce some error. We will not be able to do a perfect job for all of those. And what that means is that we actually won't be able to calculate a perfect range from us to our base stations. We will calculate some range plus some epsilon error. Okay? And what that means is that our circles won't perfectly intersect. We'll have some area and say, well, okay, there's some error in our ranging measurements, so there's some error, but we're somewhere over here, right? And the worse that error gets, the bigger my spot is. So satellite time of flight ranging, it's dead simple. Give me a synchronized timer, give me known base station locations, and I'll then calculate the position of the receiver by calculating what's called a pseudo range to each satellite. And I will do this by obviously solving for the XYZ position of me in space. And then it turns out that I'm not going to do the derivation, so you're going to have to take me on faith on this. I'll refer you to the Understanding GPS book. But what I'll do is, rather than just solve for X, Y, and Z, I'll add a fourth variable and say I also want to solve for some unknown clock offset. So our clocks aren't perfectly synchronized. We say, okay, like I think it's Monday, not sure quite when. I'll just start running a timer, and then I'll solve for both where I am and how far off I am in time from the true GPS time. So just as a note, this gives you a position in some reference coordinate frame, which is relative to the satellites. And then you convert it to latitude, longitude, and altitude by basically saying we're going to approximate the Earth by some ellipsoid and say, not going to get into that side of things because I don't think that's as important for us as UAV people. But it is worth noting that there's actually a whole bunch of interesting work that happens from where you say, I know where I am in space in some XYZ coordinate system that is centered at the Earth, and to then go to something that's what we're used to seeing on maps. Everybody still with me? Cool. So here's the first question we have to answer. Where are the satellites? Have any of you guys done like orbital dynamics, like two-body problems, that kind of stuff? So this is actually relatively simple. If you give me the 6 parameters that define a satellite orbit, which just defines a two-body problem, then I can solve for where the satellite is at any point in time. Here's our first source of big errors. This is an approximation. In the real world, satellites are affected by all kinds of things, like small gravitational perturbances, because it's not a two-body problem, right? It's not just the Earth with the satellite moving around. There's the moon, there's the sun, there's all these other things going on. But plenty of other effects. But, okay, the first thing I need to know is I need to know what's called the Keplerian elements, these 6 parameters, because I want to know where my satellites are, right? So how do I get that data? Well, turns out that one thing that GPS satellites transmit is they transmit those 6 parameters. They send down a digital signal that gives you what's called an almanac and an ephemeris, which is a low accuracy and at least think of it mentally as a low accuracy and a high accuracy set of parameters that lets you solve for where the GPS satellites are. Let's say you just turn on your GPS receiver. That means that it's going to take some time to find a satellite. When I say find a satellite now, I mean receive the data from a satellite, get this parameters, and then be able to solve the two-body problem and say, well, where's the satellite now? Why does your cell phone boot up so quickly? Well, it turns out that if your cell phone uses a GPS, it pulls this from the internet rather than try to download it from a satellite, which is obviously much faster. But what that means is, practically speaking, I usually say, well, it takes you about a minute to download this data from a satellite. So if you are pull the GPS brand new out of the box and you start it up, over the course, it's going to take about a minute from being able to acquire a satellite to actually knowing exactly where it is, the high precision. So there's usefully a little bit of information. Secondly, I said when it comes to synchronizing time, turns out we don't need to agree ahead of time on an absolute time scale, because all we care about is timing, not the absolute time, right? We care about timing how long it takes for a signal to get to us. Turns out we run our timer, and then we make this an unknown we can solve for it. And talk more about that later. Okay, so obviously we've got satellites. Now we know where they are, and they're transmitting something because we want to time the signal, right? They're sending down some data. What might this data be? Well, there's basically 2 interesting things. One is just a binary packet, a little digital signal that contains the current true time, the satellite health, this ephemeris and almanac data, which is being able to calculate the location of satellites. And this comes down at very, very low bit rate, 50 bits per second. Okay, this is like, you can't watch porn on this. This is like the slowest connection you've ever had. It also sends down basically on top of, this is then encoded using what's called a pseudo-random number sequence of chirps. So, here, let me go to the next one. What I'm going to do is I'm going to take some pseudo-random number sequence, which is literally a random sequence of ones and zeros that we agree on. It's, by saying random, what I mean is that the distribution of ones and zeros between it is about the same. It looks like noise, except I actually know exactly what that sequence is beforehand. I'll call each one of these not a bit but a chirp, and say, okay, for every bit of my digital data I want to send down at low frequency, I will then take this, what happens to be a 1023-bit sequence. I'll make 20 repetitions of this, and if I want to send a 1, I send the whole thing. If I want to send a 0, I invert the whole thing and send it. So why the hell does anybody do this? Well, it turns out that I send this PRN signal at a relatively high frequency, at about 1 megahertz, or about a million of these chirps per second. What I'll then do on the receiving side, and I will go into this in a second, what I'll go into the receiving side is I will use this, the chirps, the high bit rate, to time messages. Why is that useful? Because I know when this starts, right? I say, here's the 1023 bits. It starts with a 1, then there's a 0, then there's 3 ones, then there's 2 zeros. I know when it starts. And so if I get a message down from the satellite, I track this and I say, okay, great. I know exactly how, where the sequence starts. And so if I combine that with timing it, I can now calculate the range. Why? I haven't actually explained why this is like a smart thing to do yet. 2 reasons. So this is called direct sequence spread spectrum encoding. What you do is you take that low rate digital signal, which is the navigation message, and as I just said, you multiply that by a high rate digital signal, so you do 20 of these repetitions for every single bit. One thing that's very cool is this means that if you were to, in fact I have a nice diagram here. If you take the satellite generated code, I take the same code locally and I generate it, and then I will keep moving my locally generated copy until it lines up perfectly with the satellite copy. What happens now is I get constructive interference. For the 1 that's coming down from the satellite, I have a 1, we multiply together and add them. If it so happens that I've got noise in my signal, then that translates to the fact that some of these bits are going to be corrupted. They will be sent as a 1, but I'll receive them as a 0 or as a half or what have you. It's just analog noise on this. That's okay, because I have 1023 of these bits, 20 repetitions of that, just to send a single digital bit, which means, what that means is that I have a huge amount of noise resistance, because I can corrupt many of these small bits, and that's okay, as long as for the most part it comes out that I do line up. Then this multiplication that happens amplifies the signal. So it's what they call process gain. So you've got 1023 times 20 bits. You can get a whole lot of them wrong and still know whether I sent a 1 or a 0. So that's basically what GPS receivers do. They locally generate this pseudo-random string. They swoop it through the received signals until they find where it lines up. And you know where it lines up by seeing a huge amount of increase in the power coming out of your receiver. And now you say, cool, the signal I'm generating is starting at the same place as the signal being received from the satellite. And now, great, now my timer is running, and now I say, okay, I just received the signal, here's the start of it. How long did that take to get here? So I know that's like super fast and hand-wavy, and like it glosses over a huge amount of technical details. We can get into that later in a separate talk, but I think the important thing here to understand is what this means is that I can send an incredibly low power signal from a satellite, and as long as I'm okay by sending very low bandwidth data, I can receive these really, really, really low power signals by basically having my smart encoding scheme amplify my signals. The other thing you can do is, if you put 32 satellites on the same frequency, that's okay. They all use a different string to encode their data with. And so if I'm receiving a different satellite, it just looks like noise to me. What's kind of cute is that this is exactly the same technology that like spy agencies use, because if you don't know that 1023-bit sequence, then how are you going to decode the data? It just looks like noise. And so I don't know if any of you guys saw, but there's like this YouTube channel that people are wondering like why it exists, because there's 70,000 videos that's just like 10 seconds long with random colors. And one theory is like, oh, it's actually PRN encoded. It's actually this stuff, and it's like some spy in like, I don't know, China that's busy communicating with his counterparts in the US, and before they left, they agreed on some really long bit string. And if you have the right bit string and you multiply it by those videos, like out comes Hello Kitty or something. But kind of cool. Right. So that really is how the whole system works, practically speaking. Of course, we don't get perfect like millimeter accurate positioning. We get inaccuracies from places, and so where do those come from? Well, mainly three areas. Turns out that sometimes we don't know exactly where the satellites are. So if our Keplerian elements are slightly wrong, then our position for the satellites are going to be slightly wrong, and that error is then going to be introduced into our location. Secondly, the assumption was that the signal actually travels in a straight line at a constant speed. That doesn't always hold, right? So for example, atmospheric effects will slightly bend radio signals. And so if I thought it was a straight line, but it's actually traveling at, it's actually bent, then my distance is going to be off. Or something that's very common for us in the UAV world is when you get multipath issues. So this is where you think you're getting a GPS signal directly from a satellite, but it's actually bouncing off of some wall. There's some multipath effect that's happening. Or similarly, there's multipath interference that happens where signals take multiple paths to get to me, constructively and destructively interfere, and so reduce my ability to receive them. And then lastly, there's clock inaccuracies. Sometimes the clocks aren't perfectly synchronized. So what does that mean? Well, it means that my precision isn't that great, right? And unfortunately, it gets even worse. The inaccuracies in the ranges to satellites are made worse by the fact that, if you think about this, I'm down here on the Earth on like a little point, and 20,000 kilometers above me, there's satellites sitting. And so you can imagine that depending on the geometry of this arrangement, if I, for example, have, to go back to the foghorn example, two foghorns placed at 90 degrees away from each other, any errors that's introduced by this is fairly rectangular. On the other hand, if the foghorns are close together, then I don't get that much information out of both of them, right? And so what happens then is that the error from the one and the other is smeared out like this, and so you get much worse accuracy out of your GPS. So this is a useful number to see at for those of you guys who use Mission Planner, that like fly ArduPilot stuff, or pretty much most GPSs will report something called an H-dot number, which is the dilution of precision. That is just a ratio that says, for any inaccuracies in my ranges, how much worse are those inaccuracies in my position because of the geometry of the situation. And so that's a useful number to look at and say, well, what does my constellation look like? Do I have a really bad geometric arrangement of satellites at the moment? What can you do if that number is really bad? Well, it turns out that, as I said previously, the constellation changes. Satellites rise and fall all the time, so the best thing you can do is wait a little bit. So how do we get around some of these inaccuracies? Well, one neat thing that people do is you can calculate some of these errors. So the government spends a huge amount of time making sure that the atomic clocks that's running on these satellites are accurate. Other things like, for example, atmospheric disturbances, you can estimate. You can do all kinds of neat tricks to figure out what those are, what are the errors that's introduced, and then separately transmit that to these GPS receivers. So a lot of you guys probably know about with It's called SBAS, Satellite Based Augmentation Systems, which transmits data to GPS receivers to say, if you're in this area, here's how much the atmosphere is currently bending your signals. All kinds of like fancy stuff like that to basically try and get precision higher. And I think for like a quick overview, that's pretty much enough. But I'll have some quiz time. Yeah. So here's some questions that I basically asked myself getting into this stuff. Why does GPS not work indoors? Like, why do you guys think it just doesn't work indoors? I can listen to my favorite radio station indoors, but I can't listen to GPS indoors, strangely enough, right? So these GPS signals are incredibly weak. They're 1,000 times less powerful than the thermal noise around us, and so they just get attenuated so much traveling through any reasonable sized material that they just disappear in the noise. How can all the satellites transmit on the same frequency? Like I said, they all use different PRN codes. Same reason, how can GPS signals be so far below the noise floor? How are they so incredibly weak and you can still pick them up? Same thing, actually, this direct sequence spread spectrum technology lets you get it out of the noise. Why is GPS relatively inaccurate? This is kind of cute, actually. If you think about it, those PRN codes that get sent down, these individual chirps, if it's running at about 1 megahertz, which it is, that means a single bit, if you stretch it out, is about 300 meters long. Right now, like beaming down from these satellites, there's these 300-meter long, like ones and zeros coming down. So if I can line myself, if I can line my local copy up to this within like 1% accuracy, well, that means I'm about 3 to 5 meters accurate. If I can do it at 0.1%, then I'm 30 centimeters accurate. Turns out that 3 to 5 is about where doing a better alignment from there doesn't help you much because all the other inaccuracies take over. But lastly, why is vertical accuracy so much worse? Well, that's based around the geometry of the problem. So given a satellite arrangement, you can imagine that moves like this is much easier to see than moves like this. Okay. That's everything I'm going to say about how GPS works, but I am going to talk a little bit about the RTK GPS that we're developing with SwiftNav. So here's an insight. Rather than track this PRN sequence and do all this complicated stuff that only gives you like 3 to 5 meter accuracy, the carrier wave, the actual carrier wave that's being transmitted, which is being modulated by the rest of this data, is at 1.5 gigahertz. Now, a single radio wave that's at 1.5 gigahertz is about 20 centimeters long, compared to a PRN sequence at 1 megahertz, which is 300 meters long. So, okay, if I can align myself to within 1% of like a 20 centimeter wave, now I'm down at like millimeter accuracy territory. This sounds awesome, right? The reason why we don't all just do this immediately is there's the slight challenging problem, which is with a PRN sequence, we know where it starts, right? And that's kind of the point. We say, ye blew the foghorn now, so now I know how long it took to get here. A carrier wave is just a sine wave. Like, how the hell do we know where it starts? Turns out you can't, but what you can do is you say, okay, let's relax the problem. Let's use 2 receivers and say, well, what's the differences in the carrier waves the 2 of these see? Now, doing some fancy math, but the intuition is pretty simple, right? It's, I will track the differences in the carrier wave rather than this PRN sequence. And now as I move one receiver relative to the other, I see how the carrier wave changes, and now I can calculate the distance between them. Turns out there's all kinds of other nice things. For example, many of the errors that I talked about cancel out in this process because you now have 2 independent measurements. It does introduce one new unknown, which is the 2 receivers now need to agree on the time, which they don't. And so that is something that needs to be estimated, and that's where a lot of the challenges in building this comes from, actually estimating that. So I have a couple demos that I want to show you guys from this that's flying these on a daily basis. Keep in mind, GPS requires a very clear sky view, And so be aware that, be careful of multipath scenarios. So if you're next to a building or the like, that's a place where you can't see the entire sky. GPS signals are incredibly weak, so when it comes to actually mounting a GPS somewhere, you want to have it away from any sources of RF interference. I've spent on the order of 3 weeks chasing radio frequency interference issues where it turns out that the pixel autopilots actually have quite a lot of harmonics sitting in the GPS frequency bands. You want to mount those as far as possible away from each other. GPS requires a very accurate satellite position, and so that means getting the ephemeris down, which takes a while. So there will be an increase in accuracy kind of as your GPS goes through a warm-up phase and downloads all of those. As you fly around, keep in mind I put it in a perfectly clear spot. I take off. I have a great sky view. Now I get excited and I go like fly underneath some like archways on campus. Turns out you lose your satellites in that situation. Luckily, definitely U-Block's GPSs and most good GPSs keep all the local information cached, so when you get out from that situation, you reacquire very quickly. And I'll leave you with one observation, which is in the longer term, for people like us that's interested in doing autonomous vehicles, the solution is not necessarily to have a single great sensor. RTK GPS is a great step forward in having a very accurate localization, but this is one of many sensors you would like to consider to build a very accurate localization system, especially because some of the extreme drawbacks of RTK, being that it's GPS-based and needs a clear sky view, you can address with things like inertial navigation, visual tracking. Plenty of people are doing interesting things indoors. And then, I guess the kind of cool pipe dream that I'd like to share with you guys is imagine if we can do this, but rather than just using satellites, what if we can have more sensors in the real world that also transmit interesting digital information? So perhaps we can do this with Bluetooth-based indoor ranging. People are actually working on that, doing Wi-Fi localization by also using similar technologies, tracking carrier waves and how they change. And so this is kind of a cool time for people in this space because the localization problem has become so big that so many people are working on it, and cool things like this are coming up. So probably at one of the next fly days, I'm starting to get this RTK GPS stuff flying, and so you guys can actually see a demo in person. Okay, thanks a lot. That's it for me. That was a little bit longer than 20 minutes, but yeah, I rushed.
Niels, I'm a little bit confused on one point.
Sure.
Obviously, you want 2 receivers. Are you saying one of those receivers is at a fixed location on the ground while, at least in the quadcopter world, you fly the other receiver? Or do you put both receivers on the quadcopter?
Oh, great question. I might not have made that exactly clear. Yeah. The assumption is that only one of these receivers on the quad.
And the other one's at a fixed and known
at
location.
your drone station. It does not have to be at a known location.
Oh, okay.
But it's that
But
what
it is
the
fixed.
RTK algorithm specifically tells you is a vector between these 2 receivers.
Right.
So both of them could be moving. Not exactly sure. Well,
You need them to be
here's a
moving
useful-
relative to each other.
Yeah, here's a useful case. If the one receiver is on a ship and the other receiver is on your quad, what you probably care about is landing on the ship. So all you care about is the relative position between your incoming aircraft and the ship.
Sure.
Not necessarily, of course, there's
No,
other
no, no.
things. But in this example, both receivers are moving, but the interesting thing you get is the relative movement of the one.
And for a small $1,000 payment in 3 monthly installments, I get both receivers?
Oh, so, okay, if you guys are actually interested in the Swift product.
Yes.
Oh. You can go to the website yourself. But yes, for $900, we ship you 2 receivers, the communication system you need between them. Because you need communication between the 2, right? You need to send data from the one to the other and say, hey, here's the carrier wave I'm tracking. The other one goes, sweet, here's the carrier wave I'm tracking. I see we're a little different. So, yeah, Swift is selling this.
Final question, I promise.
Oh, sorry, what's your name?
I'm Pete.
Oh,
I sent you.
nice to meet you, Pete.
And as a sort of amateur GPS nerd. I've known about differential GPS for ages and ages, and I had that in my notion, my mental model that the Coast Guard used differential GPS, and government people and airplanes and such like as that, or commercial aircraft at any rate, had differential GPS. And here's a new term, RTK, and it's clearly some form of differential. Is there a relationship here, or is this really new, or could you just say?
Okay, yeah, a little bit of the history of this stuff. So RTK is a specific type of differential GPS solution. Differential GPS means many things. One of them could mean you also use multiple receivers, but what you do is you say, the two of these guys, I know they're 2 meters apart, I know their positions, and now I can solve for some of the errors I'm getting and saying, oh, interesting, I can now solve for some of the atmospheric effect or some of the clock offsets. And so things like SFAS or WAS is considered a differential GPS technique as well. Yeah. RTK was originally, like the original paper describing this technique is from back in the early 80s, where the insight that you can track the carrier wave, and then given 2 receivers that tracks the carrier wave, you can do this this relative vector. This technique's actually been described like a long time ago. Part of why this is happening now is that we finally have, thanks to the cell phone revolution, like small enough, high speed, low power hardware. And so the Pixie receiver that's in this front on my first slide, this contains a ARM processor, a FPGA that runs custom hardware, and an RF front end. Go for it. We'll go.
So, guessing.
I'm sorry, what's your name?
Ashish.
Ashish, please meet you again.
I'm guessing this one's using both the carrier phase and the PRN. Like the carrier phase will give you the differential, and the PRN will give you like less accurate absolute. Right?
Yes.
Also, so when if you have say 50 different satellites with GPS and GNSS combined, each one with a different PRN, then is your receiver actually generating 50 different PRNs all at the same time and checking to see if any of them are in range?
Yes, and so that's actually part of what's a little challenging, and that's why there's custom hardware on this, is that the only thing that custom hardware does is you say, here's a set of 20 PRNs, do the search by you've got your incoming signal, I don't know which PR, let's say I'm convinced I'm supposed to receive PRN number 1. I take PRN number 1 signal, and then I have to try to align those two. So it does the alignment, and the other part that I completely glossed over here is that satellites moving at high speed experiences Doppler shift, and so you have to search, you have to attempt to align both the PRN codes and then over the series of Doppler frequencies. So you have to search in this 2D space, and that's what the custom hardware does. And it'll do this for 10 channels or 12 channels or what have you. So that's actually what it means when GPS says, oh, it's like a 12-channel receiver. In hardware, in parallel, they'll do 12, they'll align 12 of these elements. Henry?
Yes. Could you talk about what are the main drivers of the cost? What are the costs?
I actually don't have insight for that. So that would be a...
FPGA will send you back.
Yeah.
As a comment from a guy in that field.
Right. I mean, so practically speaking, we can hypothesize on that. If you want to bring a product to market, you spend a bunch of time paying for development and prototyping and all that. So, obviously part of the price of this is the fact that you can order these components on DigiKey, and I don't know what their board cost is, but it's obviously less than $900, right? It's the fact that people put this together in a smart way.
So, thinking that scale would come down drastically.
I would assume that there's potentially, actually, I don't know, I can't really comment on this, but yes, scale should bring it down. How much, I don't know. That's not my area of expertise. And I don't think I'm legally allowed to comment on that according to my contract. Anyway, I know you guys want to present as well, so if people have more questions, I'll stick around, we can talk afterwards, but we want to see what you guys are up to as well.